Hi everyone, good afternoon. So yeah, a little bit about myself and the startup I work for. So my name is Kirit Thadaka. I'm from Pune, India. I graduated from the College of Engineering Pune 2 years ago, and since then I've been working with the startup Zero Labs. So we're working on getting AI on the edge. So we're tired of this whole dependency on the cloud and all your data going up to the cloud and being, sold to whoever, and none of us get any of that money, right? So we want all of your data, all the computation that happens when you use AI to remain on your device so that the data remains owned by you. And then using the blockchain, we're creating a marketplace where you can then monetize this data so that anyone who wants it can only get it from you and they need to pay you for it. So that's the product that we're working on, and we're hoping to have our prototype out in the next couple of months. So today I'm going to talk to you guys about NumPy. So I use it a lot in my work because a lot of the algorithms that we write, we first test them thoroughly in NumPy because it's the easiest way to test code, because we're obviously not going to sit and write really hardcore C++ code every time you want to test a certain algorithm, because it just wastes a lot of time. So NumPy gives us the flexibility and the ease of use of Python, whereas it's not as computationally slow as using normal Python would be. So for this tutorial, I've got a couple of Jupyter notebooks that I'm going to use, which you guys can find on my GitHub repo if you follow the link over here. So if everyone has that, then I'll get started. How many of you have used NumPy before, with a show of hands? Okay, cool. And do you guys use a lot of NumPy, or do you just do some of the basic stuff, just using arrays and just that much? Or has anyone used really advanced functions of NumPy, or does anyone use it a lot in their work? Okay, cool. So I'm going to sort of cover a lot of different functions in NumPy, from some of the basic ones to the more advanced ones, so that way, irrespective of the level of comfort you have with NumPy, by the end of it, all of us should be hopefully at the same level. So I'm going to start off with the fundamental container data structure that's used in NumPy, which is the ND array. So these are a couple of ways how you can initialize and create your array. There are a couple of different functions you can use. So obviously just passing in a list to the np.array function, you can create an array. Then if you want to create an array of all ones, then it's np.ones, you pass in the shape, you get an array of all ones, and then you do the same thing for zeros. And then a lot of times if you're ever using a loop, then you'd obviously want to be able to iterate for a certain range. So NumPy's range function is arange. So the parameter list goes start, stop, and skip. So you start from the first element, you go all the way to the last one, and if there's a skip parameter set, it skips that many elements in between. If you just pass in one parameter, it assumes that the others are 0. So you create a range from 0 to 9. Then if you want one element that can be an array or a scalar number to be repeated, and to create a certain another array with a particular shape, you can use the tile function. So here I want an array of 2s, and I want the shape to be 5 rows and 3 columns. So I use np.tile, and np.repeat will repeat each element that is in the list that you pass it. And the second parameter is the number of times those elements should be repeated. So here I've got an array with 1, 2, and I'm saying repeat it 5 times. So that's how it repeats 1 5 times, and it repeats 2 5 times. So you can see how it's different from the tile function. And another cool thing you can do is, suppose you wanted 1 repeated X number of times and 2 repeated Y number of times. In the second parameter, you can just pass in a list, or in this case a tuple because it's only 2, where you specify how many times you want each of those guys repeated. So here 1 will get repeated 5 times and 2 will get repeated twice. So that's the array that gets generated. Then there's np.linspace, where it'll create an equally spaced array between the first parameter 1, the second parameter 5, and it'll give you an array with 10 elements in between there. So here it calculates the jump to be 0.444 and so on, and then it gives you 10 elements, each element spaced out with that much value. And you can also use np.matrix to create a matrix. I never use np.matrix, and I don't really know many people who do, because you can just do the same thing with an array, and it's a lot easier. Like for np.matrix, you have to pass it in, you have to pass in the parameters in this format, and I don't know, I just don't like doing that, but it's there. It's an option if anyone wants to use it. So it does the same thing. You can just use np.array to do this. And you can also create a structured array where you can label the data that you have. So I know that's one of the big benefits of pandas, is that you can have sort of structured data, labeled data, but you can have that in NumPy as well. So here I pass in I'm passing in a list of tuples where I have the first value in the tuple to be the label of the data I'm passing in, and the second value is the probability of that label. So that's the kind of data that this array is representing. So here, that's what I first pass in. So I pass in the list of two tuples with A 0.8, B 0.2, that's my data. Now I need to tell NumPy how this data is being structured, because it's a structured array, right? I need to define that structure. So I define that in the dtype parameter. So here I'm saying that the first element in the tuple is a label. So that's the name for the first element. And the type is A8, which is basically a string, or it's 8 bytes. And then I say the second element is called prob, and the type is F8, which is a float. So then when I do that, if I had a lot more than just two tuples in there, I could get all of the labels by indexing my array like this. Just do X of label, and I get the labels. And then I can do X of prob, and I get the probabilities. So this is useful if you have a lot of tuples of this sort of structured data, and you want to get one particular feature of your entire data set. You can do this. Now probably the most powerful feature of NumPy is its broadcasting. So with that, what it's able to do is take an array of two different shapes, and if they meet certain conditions, which I'll talk about, then it's able to sort of replicate the smaller array enough times so that it is compatible with the first array, and you can complete your operation. So I'll show you how that works. So here, this is just a basic, the arrays are already of compatible shapes, so then you can just go ahead and do all of these computations without any issues. So you can just add them, you can add a scalar to it. So this is an example of broadcasting. So you have the array A, which has 3 elements to it. Then you have a scalar 1. So what this does is, when NumPy sees the scalar and it needs to add it to a vector, it vectorizes this operation. So what it does is it takes the 1 and it treats it as if it was an array of 3 ones, because that's the shape of A, and then it adds them one at a time. So it broadcasts 1 to the shape of the first operand, and it completes the operation. So the same thing's happening here, A minus 9 and A into 10. And these are the rules for NumPy broadcasting. So take a look at the rules, and then I have 2 exercises where, you guys tell me whether broadcasting will happen and the operations will go through. So these are the rules. It starts from the last dimension, so the rightmost dimension, all the way to the beginning, and it checks for these 2 conditions, whether the 2 dimensions are equal or one of them is 1. So it's 2 simple rules. You start from the right, go to the left, the dimensions should be equal, or one of them should be 1. So here, these are my two arrays. One has a shape of 20, 5, and the other has a shape of 20, 1. And I want to add these two arrays. Can they be added? Will broadcasting take place over here? How many yes? And so the rest of you think it won't get broadcasted? So yeah, it does get broadcasted, and the sum does happen properly. So the second array B, which is 20, 1, gets broadcasted to the shape of A, 20, 5, and then the two arrays are added. Okay, so this one. How many of you think they can be broadcasted? And come on, everyone has to answer this time. Yes, they can be broadcasted. Come on, what about everyone else? Okay, so how many think they can't be broadcasted? Okay, cool. So let's see what happens. Oops. Okay, anyone want to change their mind? Can be broadcasted again? Okay, cool. So yeah, they can be broadcasted. So if you look at it from the rightmost dimension over here, these two, so the two conditions state that they should either be equal or one of them should be 1. So here, this checks out, both of them are equal. Then you go to the next one. For these two, it's the second condition, one of them is 1. Then you come here, again, the second condition checks out, one of the dimensions is 1. Then here, both are equal. And then again, in the first dimension, one of them is 1. So broadcasting can happen. It follows all the rules of NumPy broadcasting. Okay, now this one. Come on, now everyone should get this. Yes? Okay, cool. Yes, they can be broadcasted. Cool. So that's it about NumPy broadcasting. So you'll find that the more you use NumPy, when you're dealing with larger dimensions and much bigger data, then broadcasting becomes really, really useful. And it's a really quick way of, it's a very efficient way of doing a computation, because the alternative would be to write a for loop and do it, which we all know is really, really slow in Python. So NumPy takes care of that. We don't have to use for loops if you're doing this properly. So now another cool thing that NumPy has is this indexing properties. So here, if this is my array of 25 elements, now let's say I want to change the shape of this so that it has one column as well. So I don't have to call NumPy's reshape function. I don't need to create a new array with the shape that I want. What I can do is, with this sort of syntax, with this indexing syntax, I can change the shape of my NumPy array. So the first part of the inside the brackets is the ellipsis operator. So this is saying all the rows. And the second operation, second parameter is np.newAxis. So it's saying that I want a new axis, I want a new dimension created here. So on all the rows, plus I want a new dimension. So here it changes the shape of the array to this. So now it has 25 rows and one column. And that's been done without using any reshape function, nothing. Just the colon operator and np new axis. You can also do the same thing by just passing none. So if I do this, it works the same way. I can both ways, np.newAxis or none, and then you can add an extra dimension to it. Yeah, so here I have created another array, and I've passed in the shape as 5 rows, 5 columns, and 1 value in the third dimension. So this is my array. And I can use this operator for my indexing as well. So now there are 3 dimensions, and if you, as you see, I passed only 2 values in here. I mean, normally we think that if I have 3 dimensions and I want to index some value in it, I'd pass in some value for each of the dimensions. So here I'm saying I want the first row, and the 3 dots afterwards expand into colon, comma, colon. So it just assumes that you want everything from the other dimensions. So here I'd get the first row, all the columns, and everything in the 3rd dimension, which in this case is just 1. So that's why I get these values. So this is the same as doing this. So I mean, so all of you know what the colon does, right? Everything in this dimension. So either putting the 3 dots or 2 colons gives you the same result, as you can see there. Now, yeah.
Does that work with negatively indexing from the back of the dimension? So could you have dot, 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 comma, -1?
Okay, let's try that out. How many of you guys think this is going to work? Yeah, it was. So, also, many times, I don't know how many of you have faced this, but I mean, I've faced this a couple of times with certain functions that I've used. I think it's happened a couple of times with TensorFlow, if I remember correctly. But when you do some computation, the array that you get returned always seems to have an extra dimension, an extra unwanted dimension. Like in the case that I had before this, the 3rd dimension just had 1 element in it, which is very pointless. It's just annoying to have that extra dimension when it's just 1 value. So there are some functions which return data in this really annoying format. So you can use the NumPy squeeze function, where it'll just squeeze out all of the dimensions that have only that are just 1. So in the case that we had the 5, 5, 1, if you squeeze it, it gives you an array of shape 5, 5. So it removes that unnecessary dimension of 1. So it kind of helps you clean out the array and makes it a lot easier to use. So this is how the array looks now. It's a lot better than how it looked before. And again, you can do the same thing over here. Now if I, for some reason, want that annoying shape again, I can use np.newAxis to get it back. And there you go. I mean, I don't know why you'd want to do this, but you can. That's the point. Another really cool thing about the way you can index in NumPy is you can pass in 2 lists, or as many lists as required for the number of dimensions you have. So in this case, I have 2 dimensions, so I'd pass in 2 lists. One list specifies the indices for the row, and the other list specifies the indices for the columns that I want to print out or take from my array. So here I've passed in 0, 1, 2, 3, 4, comma 0, 1, 2, 3, 4. So in a 5 by 5 array, can anyone just guess what they think this would return? If I indexed an array like this, the first list are the indices for the rows, and the second list are the indices for the columns, and it's a 5 by 5 array. Anyone have any idea what I'd get from this operation, and without running it on your notebook? Sorry? Yeah, the diagonal. So it gives you the diagonal. So what it does is it takes the first element of the first list, which is 0. So it says the 0th row. And then it takes the first element of the second list, which is the 0th column. And then it does the first row with the first column, second row, second column, third with third, and fourth with fourth. So that way it indexes across the diagonal. So you can pass in any combination of rows and columns that you want, and it'll do it in that sort of 1:1 way with the rows and columns, and it'll help you index through whatever elements of the array you want. You can also use the slice operator. So you can go from 0 to 2 and index everything from there. So here, I have 2 dimensions in this array, but I've passed only 1 slice to it. So what it'll do, it'll just give me the 0th to second row, because it's the first dimension, right? So it doesn't know what I want for the column, so it just assumes I want everything because I haven't specified it. So it'll give me the first and second row. So So you can see that over here. So I got the first and second row. Now, another cool thing about slicing. Now I've sliced this larger array of 5 by 5, and I have this smaller array X, which has just the first 2 rows in it. Now, let's say this was like a 500 by 500 array, and I sliced the array so that I got the first 2 rows, because I wanted to make some changes to the first 2 rows, and I didn't want to, operate on the entire large array. So now I can do this. I'll say the 0th row and the 0th column, the element over there on this slice X, I want to change to 100. So I change it to 100. So now this slice has been changed. X has been changed. How many of you think A will be changed as well? Okay, how many think A will be changed? And what do you think will be changed to? Of A. Okay, does everyone agree with what he said? And does anyone disagree with what he said?
I have a concern.
Yeah.
Like, in theory, Numpy stores everything as a one object, and that's one of the features that Numpy promotes, that they are memory efficient.
Yeah.
And that's because they're using only one object rather than multiple objects within a list.
Yeah.
So we know that in Python you can just change one point, get a pointer, Why, like if it changes, why does it change if it's only one object?
Yeah, so yeah, it does change. And the reason is that so the slicing operator in NumPy was designed to allow this. So that you can, instead of having to operate on an entire large array, you could have cases where your arrays are so large that they don't even fit in memory. We all know today with the amount of work we do with data analysis that big data is you more often than not have big data than small data, right? So there could be times where I have like a really, really large array. I want to only operate on the top left corner for some particular thing that I'm doing, but I still want my main array to be affected. I don't want to then have to copy the changes back and go through all of that. So I can just extract a slice of that array. So in this case, how I've done for the first 2 rows, do all my computation on these 2 rows, modify it over there, and then that will reflect back in the original array. So there are use cases where this is useful. Obviously in a case where it's just a 5 by 5 array, it really doesn't make a difference, but then I couldn't show you like a 5,000 by 5,000 array right now. But it does extrapolate to those to that scale. Okay, quickly, any guesses? What is the output of this going to be? Go on. Sorry?
Every other row, second, fourth, fifth.
Yeah. Yeah, so that's what this expands into. So the colon, so basically when you provide 2 colons to the parameter for the index, it goes start, then the middle is stop, and the last one is the skip in between, similar to the A-range format. So what this does is, if I've passed in nothing for the first 2, it assumes beginning to end. So it says, okay, I want to index in my rows from the beginning to the end, and I want every other row, or every other element in this dimension. So had it been 3, it would have given me every third and fourth, so on. And then we know from the previous example that when you have a list of row indices and a list of column indices, it goes in a 1:1 manner and indexes everything in that order. So here it gives me every alternate row, and from every alternate row, the first, index number 1, index 3, and index 4. So that's how I get this. Now, suppose you wanted to, instead of having this row and column indexing to happen in a 1:1 way, suppose you wanted to have it like a cross product. So the first row, the first index in the list for the rows with every element in the list for the columns, and then the second guy in the rows with everyone in the columns, and the third, and so on. So you'd use this function called np.ix_. So what it would do here is, you have 0, 2 for the rows and 0, 2, 3 for the columns, and it gives you an index like this. So what this translates into is 0th row with 0, 2nd, and 3rd column, and 2nd row with 0, 2nd, and 3rd column. So then now when I pass in this tuple of rows and columns as the index for the array A, this is how, and now you see the 100 is there because of our previous example. So this is how the returned array looks. So it's got it's indexed it like a cross product. Okay, this I'm gonna, quickly I'm gonna give you guys 2 minutes. You need to add the two arrays together and remember what is allowed for broadcasting, and then using what we know about indexing, give me the first and last element of every alternate row. So if you don't have your laptop, then you obviously can't, so try and do it in your head. If you do have your laptop, then you don't have a way of getting out of it, so. And whoever gets it first, just tell me what it is, I'll write it out, and then we can see whether it runs or not. Does anyone have it yet? Anyone? Yeah. So just tell me, I'll type it out. Okay. Yeah. So okay. So let me rephrase the question. Do this thing without using reshape. Yeah. So anyone did it without reshape? Yeah.
You can do a ellipsis, comment. Dot.
Okay.
Comment. None.
Okay. None. Okay. And then have you done the indexing as well? So then you can just add the indexing to this, because I want the first and last element of every row, right? So what would I pass into the index to get that?
Comma, open brackets, naught, comma minus one.
Oops, my bad. Yeah. Yeah. Cool. Yeah, so that's how you do it. So you first have to make sure the shapes can be broadcasted. So that means you need to add the new axis to A, then you add B to it, and then you index it in this way. So it's just like the example we did before. Every alternate row, and then you pass in the columns that you want. So that's the basics for the ND array broadcasting and indexing. So these are like the fundamental features of NumPy and what makes it really awesome to use. Now going one level above this is ufuncs and stride tricks and einsum. So stride tricks, I really like a lot. I had a lot of trouble when I first started using stride tricks. It took me a really long time to figure out exactly why it was happening the way it does, and I was really bad at it. But once I sort of got the hang of stride tricks, then I sort of started doing it just for fun, even when I didn't really need to. I just start writing stuff and then using stride tricks to create new arrays. So once I go through the ufuncs, I'll talk about stride tricks, and hopefully you guys like it too. So here I just want to start off with a small comparison between functions in Python and their equivalent functions in NumPy. So we saw before when you can create an array using a range to get a range of elements from a particular start and a stop. So here, if I want a range of 100,000 elements, so 0 to 9999, if I want to do that in NumPy, I'd just use np.arange, and if I wanted to do it in Python, I'd create the range. I'd get a generator object from range, and then I'd pass that to a list, so that gave me the entire list. And now I'll run this, and you can see the difference in time that it takes. So here it takes 1 millisecond to do it in NumPy, and it takes 6 times that amount to do it in Python. So that's just 6 times slower for, no benefit. Then for the NumPy, if you want to sum up all the elements in this array, so you want to sum up the 100,000 elements, you use np.sum, and you pass in the array that you want to sum up, and it takes 688 microseconds. And now the same thing, if I wanted to do it with my Python list, I'd have to create a loop and sum it all up. And that takes 18 milliseconds, which is an entire order of magnitude slower than doing it in NumPy, and a lot more effort to do it in NumPy. And same way, I got the function for taking the average of everything in the array, 1.38 milliseconds. And this is how I'd have to do it if I was doing it in just Python. And it takes 36.5 milliseconds. So it's 36 times slower. Okay, now if I have, so we all know that there's a Python function for abs, and there's also a NumPy function for abs. So based on the 2 examples we've seen before, answer the next question. And based on this. So the normal Python abs on minus 3.14159 takes 12.2 microseconds, but np.abs on the same value takes 62.9 microseconds. Now, based on all of that, which of these do you think is faster? Taking the Python abs on a list or NumPy abs on the list? Now, what I've done is, just to make it cooler, it's not just a list of 5 elements. It's that list repeated 100 times. So it's a fairly large list. So now, what do you guys think? Which will be faster? The first one or the second one? Pythonic or NumPy? Okay, how many of you for NumPy? And it's actually slower. Yeah. Not by too much, but yeah, it is slower. And I was surprised too when I saw this at first. So you do get the same result from it all, but why is the Python one faster than NumPy? So now, do the same thing with a small change. So instead of it being a list with 500 elements in it, it's a NumPy array with 500 elements in it. And I'm doing the same thing, the Python abs in this list comprehension and the NumPy abs, except it's on a NumPy array instead of a Python list. Now, which do you guys think is going to be faster? NumPy or Python? So NumPy. Okay. And yeah, NumPy is faster. So the NumPy abs function works efficiently on NumPy arrays. So in the previous case, what it would do is convert the list into a NumPy array and then do NumPy.abs on it, which is why you have that small overhead, whereas in the Pythonic way, it doesn't have any extra thing to do, right? It just does abs on each element on the list. So that's why NumPy abs was slower on non-NumPy data structures. Okay, now for stride tricks. Yeah. So this is the array that I have. It's just a range of 10 elements, 0 to 9. And how many of you have ever had to create like a sliding window on an array or like reshape it and then, yeah, exactly, right? So, how would you normally do it? The most intuitive way of doing it would be to, do it in a loop and then sort of create a new array of whatever shape with whatever window and slide we want, right? So that's how I used to do it as well. And then one day I was writing code and I had to send it to my boss to verify. And I had written this ugly for loop with this whole little thing in it. And then he sent it back to me with just one line, which is the line after this. And I was really confused. So I Googled it, tried to figure out why it was happening this way, how this works. And it took me a while to understand. But then once I did, that's the only way I do sliding windows now. Or anytime I have to do anything similar to a sliding window, I only do it using stride tricks. So here, So the function is np.lib.stride_strix.as_strided. So the first thing I pass in is the array that I want to create the sliding window for. Now the next thing I do is pass in the shape. So now let's say I wanted to create a sliding window over this array where the window size is 4 and it slides 2 elements at a time. So now my resultant array would be n number of rows, and each row would have 4 values in it, right? Because my window is 4. Now what you need to do is calculate how many rows this resultant array is going to have. So if I have 10 elements, I want 4 values per window, and I want a total of, the total number of windows is going to be based on how many times I want the slide to happen, right? So you can use this simple formula to get the shape of the resultant array. So the length of the original array minus the size of the window plus 1 for the number of rows, and the columns is just the size of the window. So in this case, it'll be 10 minus 4 plus 1, so that's 7, comma 4 is going to be the 7, comma 4 is the shape of the resultant array. And now the next parameter is interesting. This is the strides. So when you create a NumPy array, so you can see over here, when I create this array, it has an attribute called strides. So here it's 8. So what it's telling NumPy is, in memory where you've stored this data, to go to the next element in the list, your stride needs to be 8 bytes. So when you move 8 bytes, you'll get the start of the next element in the list. And then you go 8 bytes again, and you'll get the next element in the list. So now when you create this new sliding window array, you're essentially modifying these 2 parameters of the original NumPy array that you have. So that when NumPy reads this array back, it sees the new shape and it sees the new stride. So it's still operating on that same block of memory. So if it was just one straight block of memory before, it's still the same one block of memory now. The only difference is the way NumPy interprets this memory when you access it. So it doesn't see this memory as an array of length of shape 10, none. It now sees it as an array with a shape 7, 4. So it keeps that in mind when you ask it for an element. And now it needs to know how much memory to move to get the next element in the list, right? So now, initially when it was just a flat out array of integers or floats one after the other, it knew, okay, if I go 8 bytes forward, I'll get the next element, and so on. But now, when we have our sliding window, I'll just run this so you can see how it looks. So the first element in the list is 0. Now, the second element in the array is 1. So how much did let's say that there's a pointer at the beginning of the memory location. How much did the pointer need to move to get the second element in the list? Exactly, you needed to move 8 bytes and you got the second guy. So in the first dimension, you need to move 8 bytes to get the next element in the list. So that's how you get 0, 1, 2, 3. You go 8 bytes at a time. Now in the second dimension, which is in this case 1, that's the next element in the next dimension, how many bytes did the pointer have to move to get 1? Sorry? No, it had to move 8 to go to the next one in the row. So now to go to 1 in the column, how much does it have to move? Again, just 8 bytes, right? Because the next element in the row and the next element in the column, both are just 8 bytes away in original memory. So you tell NumPy now that my strides are going to be 8 at a time along the rows and also 8 at a time along the columns, right? Because you see the columns also go 0, 1, 2, 3, 4, 5, 6, and the rows 0, 1, 2, 3. So in both cases, it's just going 8 bytes at a time to get the next element. So my new strides is the original a dot strides, which is 8, nothing, times 2. So now the strides are 8, 8. So that's why when I pass in the appropriate strides and shape, it gives me this array. So I have 0, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, and so on all the way till 9. Now the next part of my sliding window was the slide. So here it's just got the window, but there's no slide. So what I do is I go back to the way we did our indexing before, and now I say, okay, if this is the array, give me every alternate row, or give me every row with a jump of s, which is the slide that I defined as 2. And then I get this. So I get my sliding window. 0, 1, 2, 3, 2, 3, 4, 5, 4, 5, 6, 7, and 6, 7, 8, 9. And all of this is done without creating a copy of the array. It's all done on the same memory location. So it's a really efficient and fast way of creating a sliding window. So you don't have to do any for loops, you don't have to create a new array, none of that. So it's a really efficient and fast way of doing sliding windows. So, I mean, the part that I was really confused about and which I had trouble with was understanding the strides. Because, I mean, if you look at the documentation for this function, they don't really talk well about what the strides is doing. So it's not really clear how to extend this for examples with larger dimensions. But the trick is to always like sort of picture it and look at it this way. So you look at the next element that you want in the same row and look at your original array and then count the number of jumps that you need to make to get it. And you do the same thing for the columns. And that becomes the new value of strides. So over here, if you pass in like an incorrect value for strides, so if I had just passed in like 8, you'd get an error. It wouldn't let you do it. If I passed in, it would start accessing memory that is, well, it's garbage data because this array doesn't own that memory. So it's just going to the next location and just finding random values and putting it there. So the reason why the previous time it gave us an error is because the strides had only one value in it, whereas there should have been 2 because the shape was defined as 2-dimensional. In the second case, it didn't throw an error because the shape is 2-dimensional, the strides are also 2-dimensional, but the values are incorrect, which is why it didn't give me an error, but it gave me wrong results. Yeah, and I mean, I didn't mention this before, but so the colon, I mean, this is why we have the colon operator. It's because the third operator was used a lot. So at the request of developers, the third argument was added to the 2 colons. Yeah, so you can do the same thing in 3 dimensions as well. So I have an array of shape 5 by 4. And now I want to change it so that I take, so when I want to basically change the shape so that the resultant shape is 15, 2, 2, and the strides are like this. So then now when you see the resultant array, here, so I have my first element as 0 and the next element as 1. So in that dimension, which is the third dimension, from my original array, how much did I have to move? So I moved 8 bytes because that's how the original array has been defined. In the second dimension, which is so this would be the first one out here. So I moved 8 bytes to go from 0 to 1. Then in the second one, the second one is 4. So I go 0, 1, and in the second dimension I go 0 to 4. So in my original array, 4 is in the second row, so that's 32 bytes away from 0. So that's why the second stride is 32. And then again, the second value out here, the first element is 1, which is again just 8 bytes away from the first element of the first array, which is why the resultant strides are 8, 32, 8. So if you do it this way, then it becomes a lot easier to figure out what the stride should be, and you'll very rarely, if at all, make a mistake with the strides. So that's what I had trouble with initially, and this really helped me get it correct. Yeah, so this is how the NumPy array looks in, this is the way it's defined. So it's an object that has your data as a pointer to, as like a character pointer. Then it has a descriptor for the array, it has the dimensions, it has the strides, and it has the base, and it has a flag. So here, if you want to see what those values are, you can, there's an attribute underscore underscore array interface where it'll show you what these values are. So this 1406 blah 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 is the starting location in memory for the data of X. False is a parameter that defines whether the array is read-only or not. So if it's true, that means the data is read-only. If it's false, that means it's read and write. So by default, it's obviously you can read and write to your arrays. So the descriptor is talking about the data type. So here it's saying it's, so I8 is just integer, 8 bytes. Then the shape, which is 10. Strides, none. And version is, so the PyArray object, there are different versions for that. So 3 is the latest version running in NumPy's PyArray object. So that is the version that you see over here. So then now if I do this stride tricks on it and I create a new array y, which now looks like this. So this is the new array y, which has been created using stride tricks. And now if I call this parameter array underscore underscore interface, how many of those parameters in the structure do you think have changed? So there's data, descriptor, shape, strides, type string, version. So how many of you think data will change? Does anyone think data is going to change? Will the starting location be different? Anyone? So everyone thinks it's going to remain the same? Cool. Will the description change? Yes or no? Yes? No? Cool. Will the shape change? How many for no? Will the strides change? Yes? Will the next two things change? Come on guys, will the next two things change? Yes or no? Yeah, and there you go. So data did not change because, like I said, it's operating on the same piece of memory. It's just changing this description so that when NumPy reads it back, it knows that this is how it needs to interpret this block of memory as an array with shape 9,2 and strides as 8,8. And the location of memory is the same because we're not creating any copies, we're not duplicating it, none of that. So it's the same thing. Now for einsum. How many of you have used einsum before? Okay, how many of you have used einsum? Okay, just one. Have the rest of you guys heard of einsum or like Einstein summation? Cool. Yeah. So I mean, einsum is a really cool function where you can basically do additions and multiplication using the Einstein notation for it. So here is a comparison with standard NumPy ufuncs and the einsum equivalents. And einsum is also really efficient because what einsum does is if when you're doing computation, it doesn't create any copies in memory. So it's really efficient. It's memory efficient because no additional copies are being created. So whatever operations are being done are happening on the original arrays itself. So here, if you just want to create a copy or you want the equivalent of a.view, which is just printing out the whole array itself, you do it like this. So in Einstein notation, these are my two arrays, A and B. So both of them are two-dimensional arrays of 3 rows and 3 columns. So now, in Einstein notation, you pass in a string, which in this case is I, j, and then you pass in the matrix, the array, whether it's 1 or 2, you pass in how many other arrays you want to be operating on. So what I, j means is, for every dimension, the character is the next one, starting from I. So here in this case, I have 2 dimensions. So the first dimension I refer to as I, the second dimension is j, and the array is A. So here, it's saying, give me everything that's I, and give me all i's and all j's of array A. So it gives me all the rows and all the columns of array A, which is how I get this. So it's just returning the same array itself. Yeah.
Does it matter what letters you use, or does it have to be IJK in that?
Yeah, I'm pretty sure it has to be just IJK, but we can check it. I think it does have to be just IJK. So if I do AB, or okay, it doesn't. Yeah, so AB works as well. Yeah, cool. I didn't know that. But I think it's just convention to use IJKL and so on. So in most cases, you'll find it's just IJKL. And I think we can test this whether you can use numbers as well. No, you can't use numbers. So it's characters, and I mean, in general, you use INJ. So if you want the same thing in, like an equivalent function in NumPy would be just to get the view of the array. And here you can see it's faster because it's not really doing anything. It's just giving you a view on the same array. So there's nothing. But so there are some INSUM functions which are a lot more efficient than the NumPy equivalents. But there are also some NumPy functions which are faster than the INSUM equivalents. And I have a few examples of those as well. And then we can talk about why it is that they're more efficient than INSUM. Because INSUM was written to be a more efficient alternative to the standard NumPy functions. So here, if I wanted to do a transpose, so it goes in alphabetical order. So it knows that I is supposed to be the first dimension and J is supposed to be the second dimension. But here what I've passed in is the reverse order. I've said J followed by I. So what it does is so when it returns from this function, it takes the second dimension and the first dimension and switches it around. So it gives me the transpose. So here I've got the transpose of matrix A. And if I were to do the same thing in normal Python, I get, again, I get the transpose, and it's much faster. Because when you do A dot T or A dot transpose, it's not doing any operation on the array. Just like we've seen with stride tricks, it just in memory changes the description so that it has new strides, and it returns it like that. So there's like literally no computation happening on it, which is why it's faster than the INSUM equivalent. So the same way, you can now also find the diagonal of the matrix. So here the notation is I. So it's saying in the first dimension I want, so in the first and second dimension, I want the same values, and it should return only one of them. So that's how it gives me the diagonal. So same row, same column, give me all those values. So I get that. Now what I can also do is, if in Einstein notation, so the arrow, the left-hand side of the arrow in Einstein notation is telling NumPy which dimension it needs to operate on. And on the right-hand side, it specifies how the result should look. So in general, so suppose I had like an I comma j arrow I. So what it says is all rows, all columns, but when you return it to me, return only the rows. So when you leave out a letter, it assumes that you want it to be summed across that dimension. So if you have no letters, then it just assumes you want to sum everything. So leaving out something means summation in Einstein notation. So here, if I just say I, when I had the arrow I, it would give me the diagonal. So if I remove that and just have I, it'll sum up the elements across the diagonal, because I haven't specified anything on the right-hand side of the arrow. So it just assumes I want the sum, and it sums it up for me. So here, when I did the diagonal, again you can see it's comparable. Oh wait, my bad. Yeah, so here, this is one of the things that's faster to do using INSUM. Because here, like, actual computation is happening. It's summing up values across the diagonal, and it's faster than. 1 second. Yeah, I mean, it's almost the same. It's slightly faster. It's pretty comparable to doing it either way, which is unlike the previous functions we saw, like transpose and what is the first one? View. In those cases, you could see that there was no benefit of doing it in INSUM. here you have some benefit of doing an INSUM, and with larger dimensions, you will see more of a benefit. Again, here it's just a 3x3 matrix. So when you're working in such small dimensions, it's really hard to gauge how efficient or how much of a speed benefit you're going to get. When you go into higher dimensions, higher values, then you'll see sort of an improvement. Yeah?
So apart from just comparing, how can I make a call whether this would be faster in INSUM or would be faster in just normal numbers?
So all of these, I mean, most of these functions, the ones I'm going through, like if I want to multiply these two, on larger data, it is faster. But another reason why you'd use INSUM over normal NumPy is not just for speed, it's for memory efficiency, because INSUM doesn't create temporary copies in between. So like if I had this example over here where I wanted to do the matrix multiplication of A and B. So normally in NumPy I could use the at operator, or I could use dot or matmul. And in INSUM I do it this way. So I'd say for the first array, for the first matrix A, I've called it as I comma j. That's how I've denoted the rows and columns. For the second one, I've said j comma k. So now over here, you see in both the matrices, one of the dimensions has been referred to with the same character. So what it does is, and now I've omitted that character on the right-hand side of the arrow. So what it tells INSUM is, you need to sum up the result along this dimension. So the dimension that is common on the left-hand side and is taken together, and since it's omitted on the right-hand side, you sum it up along that. So we know that's how we do matrix multiplication, right? So you take the column of the first, the number of columns in the first matrix needs to be equal to the number of rows in the second. So that's why you have ij and jk. And then you do an I and k, because along the columns of the first and the rows of the second, you do your summation. So here, you have INSUM is actually faster. And ran it again, and now it's slower. But I mean, this makes more sense the previous one, because np.dot is not written in normal Python and NumPy. It's optimized and written in BLAS. So np.dot is supposed to be one of the faster functions in NumPy. So INSUM, when it was written, from then itself it was known that INSUM would not be able to perform comparably to np.dot because it's written in Python and NumPy, whereas np.dot is written in BLAS or MKL, whatever your platform supports. So it's very optimized code, so that's why it'll be very hard for you to find functions that are faster than dot, and not sure which are the other functions that are written in BLAS, but then there are, like as you all know, many NumPy functions are written in low-level C and BLAS, which is why it gives you that big speed up as compared to normal Python. So here, like one area where INSUM is useful is if you were to take an example of a convolution operation. If you want to do a convolution operation just in NumPy, you can do it using Stritrix and INSUM. So, I mean, does everyone know what convolution is? Okay, I mean, just in case there's anyone who doesn't know what convolution is, this is how it works. So, on the, so on the bottom, you have the first matrix. So I'm just going to call that matrix A. On the top, you have the kernel. So, or you can call it matrix B. But in general, when you talk about convolution, you always have a matrix and you have a kernel, and you apply the kernel onto the matrix. So here we can just talk about it as A and B. So what it's supposed to do is so if you can see, the blue elements is the first matrix and the green one is the second one. So when you do convolution, you expand the boundaries of the first matrix, and there are different schemes that you can use to expand it, either with all zeros, or you can just replicate the elements that are at the boundary of the base array. So you increase the size, and then you take the top array, and just like it's showing over here, you sort of superimpose the top array onto the bottom. you do an element-wise multiplication of all of them, and then you sum it up. And that becomes the value at that point. And then you slide it to with whatever slide you want. So here it's just doing it with a slide of 1. You can change it to a slide of 2, 3, 4, whatever you want, and you'll accordingly get the new shape of the resultant. So then here it slides it, again does the multiplication element-wise, sums it up, and that's the next element in the resultant array, and so on. So that's how the convolution is happening. So now if I wanted to do this, so here, here's another example of how convolution is happening. So here in this scheme, it's been expanded by multiplying with all zeros, adding all zeros to it. So when you take the kernel, which is on the left-hand side, you take, starting with 22, 15, 1, you would initially multiply it with the top left. So you would initially take this and multiply it with these elements. Then you take this and multiply it with the first column onwards like this, then the second, and so on. Then you come down here, multiply it like that. And then you finally come down here, multiply it like this. You do an element-wise multiplication, and then you sum it all up, and that's the value at the location. So here if I had this matrix. So this is the matrix, and this is the filter that I want to apply to it. Now I want to do a convolution of this small filter of 3 by 3 onto that larger array of 5 by 5. So the first thing I need to do is I need to, so using NumPy, I take the first array and then I create a bunch of submatrices so that I can take the kernel and multiply it onto each of the submatrices and then sum it all up, and then the resultant would give me my final output. So to create submatrices is just like creating a sliding window, right? So you have a particular window, in this case it's 1, and you have a particular shape that you want the resultant to be in, and we can use stride tricks for that. So here, for that, you need to, so similarly to the previous example of stride tricks, we computed the resultant shape by taking the length of the original, subtracting the window, and adding 1. So here I take the shape of the original because it's 2-dimensional, subtract the shape of the filter, which is the window, and I add 1 to it. So that's how I get the resulting shape. And for the strides, in this case, I just want, so here, I'll just print this value out. Yeah, so 3 by 3 is the shape of the filter, and now the resultant convolutioned, the convolved result would have a shape of 3 by 3 by 3 by 3. So if you were to take the original 5 by 5 array, then take the 3 by 3 kernel and actually, like using pen and paper, try and figure out what the resultant would be. If you were to take the first one, then slide it with 1, multiply it again, and so on, you would see that the resultant array would have a shape of 3 by 3 by 3 by 3. This is not the resultant array, sorry, the submatrices that you're multiplying would have a 3 by 3 by 3 by 3. And when you need to stride over the submatrices, these are the strides again. Again, it'll be a lot easier to visualize if you, took like your pen and paper and drew out the matrices. Then you'd be able to see how the resultant shape and not the resultant shape, the shape of the submatrices and the strides along the submatrices would be like this. So this is how the submatrices look. So the first submatrix you need to multiply the kernel with is this, and the second is 1, 2, 3, 6, 7, 8, 11, 12, 13, and then 2, 3, 4, 7, 8, 9, 12, 13, 14. So if you look at the first array of length 25 shaped as 5 by 5, you'll see that the first when you draw it out and you take the top left corner of 3 by 3, that's what you get. And then you move it by 1 to the right, and those 9 elements are what you get. And then again you move it, and these 9 elements are what you get. And in that fashion, you keep sliding it across the original array, and those are the sub matrices that the second matrix of 3 by 3 needs to be multiplied with. So using stride tricks, I've expanded not expanded technically, I've changed the view on this array so that it's treated as an expanded version of the original, so that it's easy now to then just multiply the second matrix onto this. Yeah.
Was data copying done in the process of?
No, I've used stride tricks, right? So there's been no data copying. It's just those parameters of strides and shape have been changed so that when NumPy interprets it, it knows to interpret it like this. So that's what makes it really efficient, right? You don't have this unnecessary extra memory wasted. Now, I use einsum to do the multiplication. So the first ij is talking about the convolution filter, which is the second, the smaller matrix. So here I'm saying I have 2 dimensions in there, inj. Now I want my submatrices, again, was a shape 3, 3, 3, 3, right? So that's why I've used ijkl. Now I want so here I have, like here, if this was so now if I'm talking about just the last guy, then I want to multiply the filter with these values, right? So I need to multiply it with all the rows and all the columns. So that's why INJ are common, and they're left out on the right-hand side, which means they're summed up along these values. So then now when you print out the convolved result, this is what you see. So the last element, 182, if you look at the convolved, the filter, which is 110, 123, 011, 182 would be that filter multiplied by this submatrix. You multiply it element by element, and then you sum it all up, and you'd get the value 182. And the same way for all the other values, you'd go to that submatrix, multiply it with the kernel, sum it all up, and that's the value you find in your convolved result. So that's how you can do a pretty intense operation like convolution just in NumPy using einsum and stride tricks. And here neither einsum nor stride tricks uses any memory copies to do it, so it's very memory efficient. So if you were doing this on much larger data, you wouldn't have the unnecessary overhead of creating a whole bunch of submatrices and just wasting a lot of memory in the process. So it's a pretty efficient way of doing an operation like convolution. Yeah.
That 4G array of indices might be quite big.
Sorry?
The 4G array of indices might be big.
These aren't the indices. These are the actual values in the array. So these are the actual values of the array that I want to multiply with the kernel. I mean, yeah, they look like indices because it's 0 to 25, but this is the actual data that I want to multiply with the kernel matrix. Okay, so this is an exercise for all of you to do. So you have an array, yeah. Sorry? Here I didn't. I mean, if you want to do that, then you could use one of the NumPy functions to do. So there's a numpy.pad function where you can specify how you want the padding to be done, like how many elements on the left you want padded, how many on the right. So that depends on the sort of why you're doing the convolution. So if the use case you're doing needs the convolution to be done with elements padded around, then you'd have to pad them. You can use numpy.pad to do it, but here I was just showing you the basic convolution operation, which is you apply the sliding window on each element of the array. But yeah, there's a numpy.pad function where you can do it. So yeah, this is for all of you to do. So array of 15 elements. You have to window it so that the window size is 3, the jump is 2, and then find the mean along the row of the last 2 elements in every alternate row. And yeah, that's the answer. So all of you try it, and I mean, hopefully all of you get the correct answer. So I'll give you like 2 minutes to try this out, and then I'll move on to the next thing because we're running short of time. So yeah, just tell me when you're done with this, and then we can move on. Is anyone having any trouble with this? Then, I mean, I can help you out after the tutorial. So, yeah, I'm just going to move on to the next topic. And, I mean, all of you make sure you try this either now or when we're done. And if you need any help, just feel free to talk to me anytime you see me. So, so now I'm going to... Yeah. So, if any of you have ever tried creating your own sort of class that you want all the properties of NumPy to be there, but then you have some additional features that you want to sort of impose on this class, then NumPy mixins is a pretty cool way to do it. So, like, I'll tell you some example of how I've used it. So, while doing some of the work that I've been doing, we needed to basically create a data structure that follows a certain property of all values. When you take the sum, they should be 1. So irrespective of the size of the array, the shape of the array, when you sum it all up, the value should be 1. So that was the property that this data structure always needed to follow for it to be valid. At the same time, I wanted to be able to do NumPy operations on it. I wanted to be able to use np.sum and np.add, subtract, all of this stuff. But I still wanted this property of the sum should be 1 to be maintained. So for that, instead of creating my own class where I had all of these functions defined on repeatedly, like I'd have to create my class, call it, in this case, probably distribution function, then create a function called add, which would add all of them, and then sort of make sure that this property was maintained. And then if I needed to use it, I'd do my class dot add on these two on the two arrays. But instead, I want the ease of being able to do np.add and np.mean and whatever other NumPy functions I want, but I also want my property of the sum to be 1 to be maintained. So for that, when you create your class, you inherit from this np.lib.mixins.ndarray operators mixin. So what this does is, it brings in all of the NumPy ufunc capabilities. So ufuncs are np.add, subtract, multiply, divide, all of these functions, they're unary functions. So all of them come from mixins. So now all of these functions are available to my class. And I still have the flexibility of imposing whatever properties I want and whatever unique features I want onto this class. So here, I do that through the init. So here I've defined this as, I've defined array init called PDF, where it would be an array of probabilities. And as we all know, probability value should never exceed 1. And now I want to add one more step to it. So I've made it a probability distribution function. So the sum of all of these values should always be 1 for it to be valid. So I just make sure that check has been handled in the init so that when you create an object of this class and you pass in data to it, it should follow this property. Now, if I did like an np.add on 2 objects of this class, NumPy doesn't care what these arrays are, right? NumPy doesn't care that I want them to be summed up to 1. That's on me. So if I were to just use np.add on 2 values, I'd very likely get values that don't sum up to 1. So how do I impose this property on my class? So with np.lib.mixins, you get access to this function, underscore underscore array underscore ufunc underscore underscore. And this is the function that is called whenever you call a NumPy ufunc function. Like if you call np.add, it goes here, and then it does the add. And if you call subtract, it goes here, and then it does it. So if you see in the parameter, you have, so in the parameter list, you have ufunc method, inputs, and kwargs, which takes care of all the parameters you'd have if you were to call a np.add or whatever, right? You'd pass in the inputs, then the method is np.add, you'd pass in your kwargs, and it would do the addition. So this is where you add in all of your extra logic to make sure that this object and this class conforms to your rules, even when you do NumPy functions on them. So here the first thing you do is, if you, with np.add and all these ufuncs, you have the option of passing in an out parameter. So if you want to add 2 arrays and store it in a third array, you can pass in the third array to the np.add call, and it would store it there. So here the first thing you do is check whether the ufunc has any of these arrays that you need to store the data in, and if it does, you basically extract all of those arrays from the KW args. Then what I'm doing is I'm making sure that whatever data is being passed into these functions should conform to my rules. They should be of the data types that I support. So here I've defined self.handled types to be just an ND array and an object of type probability density function. So I don't want to be able to add a list to this. I don't want anything that's not an NumPy array or a PDF object to be allowed in a ufunc. So none of that can happen. If anything that's passed in, so if I try doing an np.add on a NumPy array not a NumPy array, if I try doing an np.add on an object of my class with a list, it would just give me a not implemented error because that's not something I support. Now the next thing it does is I need to extract the PDF object, the PDF variable, from all the parameters that are of type probability density function. Because if it was a NumPy array, then I'd just take the array itself. But if it's a object of this class, then my input is not the object, it's the array that's part of the object. So I do x._PDF if it's an instance of probability density function. Otherwise, I just take x. Because by this point, you know that it's either going to be a PDF or it's going to be a NumPy array. So there's nothing else you need to worry about. Now here, now I need to set the out parameter. So now here, the out parameter would be the array of the object if it's an object of the class, or it would be the array itself if it's just a NumPy array. So that's the check I put in over here. So if this was just a normal NumPy array underscore ufunc function, you wouldn't have this x.pdf out here, right? Because it would just be x, because the input that's coming in is just a NumPy array, and whatever data needs to be put in there will just go into the array itself, right? But because I also want to handle objects of this class, I need to change the value so that it's the object, it's the array that's stored within the object that is being passed into the ufunc further downstream. So then now that I've done whatever modifications to the input and output that I need to, I have my inputs are just NumPy arrays and my output is a NumPy array, right? Because I've extracted the NumPy array from the object that's been passed in. So now I can safely call the NumPy ufunc because it's just going to operate on two NumPy arrays. So then I do that through this. So you call the get attribute, use the get attribute function, and you pass in the ufunc method, and then to that you pass in the inputs and the optional arguments, and then whatever result it returns is the result that you'd get when you added the underlying data of the objects and the NumPy array with whatever method you're using. Now when this returns, there's no guarantee on whether my data will all conform to my rules of adding to 1, right? So I need to impose that rule on it, which is why when I return it, I create an instance of my object and pass in this data to it, so that when the instance is created in my init function, it handles the case that the sum is not 1, and it sums it to 1 and then returns it to me. So this way, when I add an object of my class to the NumPy array, or I add two objects of my class, I can use a standard NumPy ufunc and still get a result that conforms to my rules. So here, this is the PDF that I've created. It's just an array of 0.25, so it sums up to 1. And now, if I want to use NumPy's ufunc on it, I mean, you usually wouldn't be able to do this, because if I hadn't defined that ufunc intercept function and I hadn't inherited from mixins, numpy.add would throw an error because it has no idea what two objects of type probability density function are doing in its function, because it doesn't know how to operate on it, right? It doesn't know how to interpret it. But now, since I've defined that, the first thing it'll do is it'll go into my definition of ufuncs, and then it'll add it together. So here, the resultant is still So here, the original array was, in this case, it was actually 0.5. It was 0.5, and the shape was 2, 2. So when you add it together, it became 1, 1, 1, 1, right? If you add 0.5 plus 0.5, became 1, 1, 1, 1. When you add those together, the sum is obviously greater than 1. So when I return from array underscore ufunc, I create a new instance of the class, right? So when it creates a new instance of the class, it comes here. It sees that the values don't add up to 1. So it divides it by the sum. And therefore, now the sum has become 1 because it's 0.25 plus 0.25 plus 0.25 plus 0.25. So here you can see how when you call this function, it's going into my array ufunc call. Yeah, I don't have my debugger set up here. But when you call numpy.ufunc, the first thing that it does is it comes here. Then it'll do all of this. It'll extract the PDF object from, the PDF variable from the object, and it'll pass that into the np.add. And then when it returns it, it'll again pass it back to my object so that it does whatever conformance checks it needs to, and then that's the result I get. So that's how mixins work. So you can use this to create sort of more complex classes that will be able to support NumPy functions, but then also have any additional properties that you want to have. So one more thing I wanted to talk about is memory mapped files. So if you're ever working with like really, really large data in NumPy, so you can use memory mapped files. So here the shape of this array is 10,000 by 10,000, and I'm not sure if this is actually supported or not, like if you wanted to do it normally, but if you go to larger array sizes, you'll find you get memory errors because NumPy can't allocate that larger chunk of memory for your object. In which case you'd want to, so what you can do is just have that data in a file, and then using NumPy, access portions of that data from the file, do all your modifications, and then it'll get written back to that file. So instead of creating a big chunk of memory while you're doing your program, you'll just use that file as your memory. So here I've created a file called big file, and it was initially created to have all zeros in it. Sorry, all ones. So if you look at it, this is the file. This is a large, it just printed it from memory, so it's mapped to this. So this file is mapped to this piece of data where it's all ones of shape 10,000, 10,000. So now if I wanted to sort of operate on this portion of data, I just wanted the first two rows, first two columns, and I'll do whatever to it. So then now here I can, let's say I wanted to change the first element of the file to 100. So I can just take that small section of the file, change it to 100, and then now that change persists in the actual file. So this way I don't have to load my entire data set into memory to operate on it. I can leave it in this huge file and operate on specific chunks of this file and still have those changes persist if I want to use it later. Yeah?
Where did you specify the chunk that you wanted? Was it the 10,000?
No. So here is where I create the sort of the pointer to the file. So the file name is defined as big file. And so I've created this file before because, I didn't want to create a 10,000 by 10,000 object now. So I created the file. I've said the type of data in this file is float 32. The mode is read-write, and the shape is 10,000 by 10,000. So then this is just a pointer to that file in memory. And then here is where I specify whatever chunks I want to operate on. So here I've said I just want to change the first element. But I could take like the first 10 rows and 10 columns and then do whatever operations I want on it, and it'll persist in the file.
You'll load that
Yeah, it'll just load that small chunk. So instead of loading your whole data, you can save that by just working on these chunks.
Is it a specific data format?
No, it's just a normal array, right? You create a normal array, a normal NumPy array of.
The big farm that you have, the farm name, big farm.
Yeah, there's no data format. So what I did is I created a NumPy array of size 10,000 by 10,000, and then when you do this np.memory map, you sort of just I'll show you. Well, I'm sorry, if I got your question correctly, you meant how did I create this data?
Yeah.
Okay, I'll show you. I have the code. I'll show you after. It takes a bit of time to do it. So, I mean, I can show you offline if that's fine. Yeah. Okay, so as I'm done with my NumPy tutorial, I hope all of you guys liked it, and I really hope that some of the stuff that I talked about today will be useful for all of you in the work that you do. And if any of you have any questions or need any help with anything, feel free to contact me outside of the session, and I'll be happy to help all of you. Thanks.